Tonight's talk will be Control Logic, the Backbone of AI Data Center Infrastructure by Aushim, Senior Software Engineer at NVIDIA. So I forget this sometimes, so a reminder to myself and maybe other people, please silence your cell phones. That's appreciated. So we're San Francisco Bay Area ACM. ACM is the Association of Computing Machinery, the professional society for computer science. So a lot of the computer science journals or conferences would be by the headquarters office out of New York. They were founded in the Bay Area in 1947, and our local professional chapter was founded in the Bay Area in 57. So we're a nonprofit 501c3. There's a $20 annual membership. We have upcoming talks on our meetup site. Look for SF Bay ACM for San Francisco Bay ACM. And we have, I haven't counted lately, I don't know if it's 230 or 240 of our more recent talks are on our YouTube channel. So YouTube, sfbayacm.org. We aim for 2 monthly meetings. That kind of depends on speakers we find and things like that. We generally do a general computing meeting and a data science or an AI meeting. We also like to support networking, job hiring announcements. Sometimes we do joint meetings with other groups, IEEE or various other AI groups. So knowledge is not a zero-sum game. If you like us, you can give us a 5-star review on meetup.com. So there's a section where it lists the stars. If you have a good experience, then go ahead and click on there. We have some sponsors. So one sponsor is RXM for cloud native and AI training and consulting. Let's see. So they do training and certifications. They can go to your site. So I know Ron, one of the organizers in our group, he's gone on to for a week-long training on Kubernetes, for example, at a company location in another city or over in Europe or different places like that. So they specialize on consulting and training. Another sponsor is FrontEgg. So they handle identity management and software. So thank you to FrontEgg for your sponsorship. You can use chat in Zoom if you're remote. You can text questions, and I'll moderate some of the questions, and I can ask the speaker. Also for technical issues. Also, if you're remote and you want to share a job announcement that your company's hiring something in computer science or AI, then that's always of interest. So for people in the audience, if you ask a question, on some occasions, the person is tempted to do like a 4-minute statement and a 5-part question. I ask the speakers to repeat the questions for the audience and for the recording. So if it's something that is too long for the speaker to remember, please be kind to them. Have something shorter or something easy enough that they can repeat for the audience. We have an ongoing call for volunteers. So we have about a dozen or so volunteers that help with different roles, from pizza to working with location sponsors to marketing. I'm involved in working with a lot of the AI speakers. I'm one of other people. So it's one of those things, many hands make light work. We have an honor system, jar for food. So we're just, the $20 annual membership doesn't pay for too many slices of pizza in a year. So I kind of cover that as you go. We just like to make it comfortable so people can come after work and show up and socialize and visit with people. So we have some upcoming events. Saturday and Sunday, June 7th and 8th, there's a AI summit for young scholars. So it's 2 days on a weekend. The first day is for workshops at Cupertino City Hall, and the day 2 is a hackathon at Maker Nexus. So this is more supporting the high school kids for STEM education, but we mention it here if anybody wants to volunteer to help the kids in a hackathon, help ask questions, give other support. We do other things, like in March, we were involved in a Synopsis Science Fair, where we reviewed maybe 1,000 projects, and we gave first, second, third place awards for students in 6th grade to 12th grade, both to the students as well as to the science teachers. So we are not just a meetup, we're trying to help with STEM education as well, part of our nonprofit education. On Wednesday, June 18th, here at Valley Research Park, there's a talk on digital storage and memory for the Earth and beyond. So that will also be our annual election for new board members. So we have a president, vice chair, and treasurer, and then we have 3 members at large that are voting. Then in July 16th, we have in-memory computing, SoC, with multi-level RRAM to accelerate AI inference. So if this audience that's interested in data structures, you might be interested in that talk as well. For details, again, see the meetup site. So to introduce tonight's speaker, he'll be covering a primer on emerging tech on open source software for AI and data center management, talking about embedded controllers, deal with massive telemetry data generated by AI, large volumes of data being generated, open source communities driving data center enablement. GPU-centric computing is driving software design. NVIDIA's been doing a lot of very good things. I went to the NVIDIA GTC with my closest 25,000 AI professionals a month or 2 ago. Asynchronous programming strategies for real-time workloads, tech challenges and future scope for data center buildouts. As his background, he's a senior software engineer at NVIDIA in Santa Clara. He's an alumnus of Carnegie Mellon University. For the past 3 years, he's been designing data center software, solving challenges in scale and latency. He wants to break the barriers of fault-tolerant computing and optimization of compute node infrastructure for AI workloads. And he's also listed his LinkedIn profile there. So please help me give a warm welcome to Aushim.
Thank you so much, Greg. Thank you all for coming. I think that was a great introduction of what I do. Maybe it was a little, it portrays me in a better light than what I actually do on my day-to-day. In my day-to-day, I'm just a senior software engineer, I bet like most of you. But with the surge of requirements for compute and data center infrastructure that's taking over the world, I'm just excited to share some of my work and some of the open source technologies that exist in the form of either firmware and software stacks or people contributing to actual hardware infrastructure that brings up data centers across the world. Before that, I need to change my slides.
Thank you.
Okay, so to get started, I want to give you a quick introduction of myself, apart from the nice professional one that Greg did. So I live in San Jose, and these are just a bunch of assorted pictures that I think describes me well. For those that know me, the first one is a very overused picture. That's my display picture on Slack and everywhere else. So I think it has a very tight connection with who I am. The second is GTC 24. And the reason I've put this image up is because it was the first conference I attended and I presented at where I really saw the scale of AI take off. So ChatGPT came somewhere around 22, right? And 23, GTC 23 didn't really have the runway to display both the innovations as well as upcoming technology that was starting to take shape in 22. But 24 suddenly saw a boom from people showing consumer GPUs, for example, to suddenly full rack solutions. So you saw liquid cooling, you saw high density power equipment, racks, compute nodes, all of that on display. So that's when I really got a taste of how my work was impacting industry, not just here locally, but there were companies from all over the world, especially Taiwan, China, and all the guys pioneering data center infrastructure. Does anybody know what that picture with the waterfall is? If anyone's into hiking? Yep. So that's Vernal Falls, one of my favorite hikes in Yosemite. I do that as often as I can, but it gets a little crowded, as you guys know. The fourth is some random place in Virginia where we ended up camping and we were we were blessed with a view of multiple shooting stars. And I just put it on there because it reminds me of how small we are and the kind of problems at scale we can really solve, maybe someday through engineering. Um, that's me, my graduation picture at CMU, where I graduated with a master's degree in electrical and computer engineering. Um, and yeah, I think that's a good enough introduction. So what excites me about engineering? I've always loved taking things apart, trying to understand why something exists in its current shape or form. So the whole motivation for me was, why do we do something and how we do it? So in hindsight, I think just the taking apart and putting together was the whole driving factor throughout my college days. And when it comes to collaboration, I really appreciate people who can keep me honest. So if I make a mistake or if I need to gain knowledge about something, um, it's up to you guys to say you're wrong, and I love to learn. So, uh, yeah, thank you, Greg, and thank you, Liana, and all the organizers for setting this up and giving us a platform to network and form friendships. Three is I dislike being put inside a box. So I know what my job description is, but uh, I might be working on like platform software, but I think we are expected to do much more than that. At times, I'm a hardware engineer, at times, I write machine learning code. So I really like breaking the barriers of the box that we usually put in. And just before we go ahead, a disclaimer that I'm doing this as a volunteer because I just love sharing my excitement about advances in tech. Um, these views do not represent those of my employer, and everything I talk about is already in the public domain. A lot of it is open source. And I know we won't be able to cover everything. This is more like a beginner to intermediate level talk, but I'll stick around so we can get into the weeds of system engineering or optimization theory and stuff like that. I always like to start with a little bit of context. I think before we get into new age computing, it's good to think about where we were like 200 years ago. Anybody know what this is? It essentially was, but it's called the difference engine. So it was built in the 1820s by this guy called Charles Babbage. And the reason I put this up is because it's about 8 feet tall, and the dimensions are similar to a GB200 rack that you see today. We'll go into the number of teraflops that you see in today's supercomputers, but this entire contraption was fully mechanical, and all it did was solve polynomial functions. And its main use case was, well, now I say all it solves is polynomial functions, but I bet it was a big deal back then. Um, it was used in the British Navy initially to chart paths for navigation on ships. Um, and it had like multiple wheels or gears, and each gear at the bottom represented a digit. So it used the decimal system. You had 10 such wheels. And this thing predated the IC engine. Um, and then we got a little ahead of that with the Hollerith tabulating machine. And the reason I love this thing is because it was the first commercial use of computers. Um, it was used in the 1890s to do research on census. So it collected information using those punch cards from families based on their demographics. And it reduced the census calculation time from a couple of years to just a few months. And that allowed people to, not people, but economic policymakers to reduce that turnaround time from exercising a policy over a few years to just a few months. And this draws a parallel with AI because people were skeptical of this, just like people are skeptical of AI stealing jobs now. And we've seen the kind of uh, explosion in the tech industry we've seen since these mechanical machines. So uh, I'm just hoping for the best in the case of AI as well. flash quiz. Does anybody know what this company ended up being called? Yes, exactly. IBM. That's pretty cool. Okay, last history slide, I promise. George Stibitz created this mechanical digital logic system, which used actual switches instead of transistors uh, for digital logic design. And he used a few light bulbs, batteries, and metal strips, stuff that he found on his kitchen table, apparently. And obviously, these were bulky, slow, power hungry because of the size. But they really shaped the landscape of logic design. So you could create discrete digital logic and shape digital modern computer architecture. Okay, and then we had some cool milestones like the invention of the transistor, C programming language, personal computers, and here we are in the 2020s. From the internet, we have now progressed to generative AI, where we actually try to mimic human behavior in an intelligent fashion through the use of tokens. Like you use electricity to convert existing data into some form of tokens or decision making or intelligence. So just to compare where we are now, this was the image on the left is the first Cray supercomputer, which was manufactured in New Mexico by Cray Research. And you can see that it could compute a whopping 160 megaflops. This specific MacBook is 3.6 teraflops, which is like a magnitude of 10 difference. And the Alps supercomputer, which is based on Hopper GPUs, has a magnitude of 5 difference between the MacBook Air and the supercomputer. So yeah, we've come a pretty long way. And a lot of it has to do with this thing that is called a GPU. So modern computing has evolved based on the kinds of operations that we need to perform to manipulate data, right? And the fundamental driving force has been the ability to perform repetitive tasks using an instruction and on a batch of data. So this is exactly what graphics processors do. A lot of our modern use cases are just computing hashes, matrix operations, and graphics, which are SIMD, or you provide one instruction and then you can operate on a bunch of data at once, which allows you to offload or ship compute to a different processor that can crunch through it. So this was a nice analogy I found online of a GPU and a CPU. You can think of the GPU as a large ship which is able to carry a lot of workload or data at once. And the CPU is more like a jet, which moves faster. It has more powerful cores. But the reason you need both of them is because the CPU is the one that can serially execute instructions very fast, right? Fetch, decode, execute, blah, blah, blah. And because of its nature of being able to weave through these instructions, the CPU is today used a lot as an instructor to the GPU. So you can do things like load data, perform SIMD operations, and then unload data. And the GPU is now, it's taken the limelight in terms of being able to process so much at once. It's just a data cruncher. So the CPU is more of an overseer, and the GPU is more of a data specific batch processor. So to go a little into GPU architecture, I think it's interesting to know what a GPU looks like inside. A lot of you might be working with GPUs on a day-to-day. But at the heart of the GPU is that small green box that you see, which is called a CUDA core. And the CUDA core has a very simple function. It does a scalar fused multiply and add, which you can just think of as AX plus B, where X is your input data and B is some deviation from that input data. And you have a lot of these cores at once, right? But the real, I'd say the real innovation comes in how you can synchronize all these cores to operate at once. And that's the reason you have this structure that is followed inside a GPU monolith, which is the outer gray box, which represents GPCs or clusters. You usually have 6 or 7 of those, depending on the architecture. And within that larger gray box, you see the smaller black box. It says SM. I don't know if you can see it from there, but those are the streaming multiprocessors. And the streaming multiprocessors are the things that contain logic for synchronization of caches, hardware interconnects, and data sharing between these CUDA cores. And when you execute a CUDA operation or a batch multiply add or anything like that, at least in the older architectures, all the CUDA cores were abstracted as a warp, which means you can have a set of cores, let's say 32 cores, which operate in step. So for every clock cycle, you have those CUDA cores generating an output, maybe AX plus B, for that specific clock cycle. And now things are a little different. You can have out-of-step execution, which means even within a warp of 32 cores, you can have different out-of-step execution of the same SIMD operation. But yeah, you also have something called a ray tracing core within the streaming multiprocessor, which are used mainly for graphics. And you have the tensor cores. Tensor cores are used for matrix operations. As you know, they are extremely important today, where almost every machine learning statistical operation requires us to either scale, transform, or add, multiply matrices. And so the tensor cores are the ones that would do that job. So if I had to just make a few points about what we learned earlier, it's that CUDA cores do scale, fuse, multiply, and add. Consumer GPUs mainly operate on floating point 32. In 32, you can do bit shifts, negative numbers. So you can think of it as a very archaic CPU core, but they're all synchronized. So you can do batch operations. A tensor core does matrix multiplication, and then you have ray tracing cores, which do ray tracing stuff. So ray tracing is basically, assume you have a graphical scene and you want it to appear more realistic based on which objects reflect light and how they reflect that light. So instead of simulating every single ray of light from the source to hit an object and then into the scene camera, ray tracing algorithms do the opposite, which is you shoot a ray of light from the camera and you estimate what color that point in the image should have based on lighting conditions or based on shadows and its position. So all the realistic games you see today are made possible because of ray tracing cores. Yeah, so that brings up an interesting question, which is how a consumer GPU is different from AI chips, right? We hear this word AI accelerators a lot. And the main difference is this: you have more powerful tensor cores because almost everything is a matrix multiplication today. You have more number of tensor cores because you want to do more batch processing in matrix form rather than in scalar fused form, which is AX plus B. Floating point 64 is important for everybody working on machine learning applications. You cannot always quantize your gradients, right? When you do backpropagation, your precision is very important in determining model convergence. So if If you just study SGD, you'll realize that you'll probably be stuck at a local minima if you quantize too much. And of course, there's not much use for ray tracing cores. Instead, you just have more tensor cores. Okay, so the GPU as we know it went from that small consumer product to something much larger than life now. So while it suffices to do a lot of graphics generation on standalone systems with dedicated GPUs like a 4090, most people would want to do training on their own dedicated AI data center system that we would call either a rack on a smaller level or a compute node at an even granular level. So we'll look at that video, which gives us a little more insight on how things are set up in a system sense. Since you have a basic idea of what a GPU does, the point of creating these AI servers is a little different from data centers, right? Data centers manage a lot of storage, networking, and a little bit of compute. But AI data centers are more focused on how do you bring data towards an abstraction of a GPU in some sense. You could think of this whole data center as a gigantic GPU. It's just a very complicated system that enables you to run compute all at once. So what used to be a server or data center is now just that giant dual die GPU. Hopefully this plays. Oops. Okay. I hope that conveyed the scale of data center infrastructure that we operate on today. By we, I mean the industry in general. So the state-of-the-art solution today is to abstract 72 dual die GPUs into a single system, which you can literally use as one GPU from a user's perspective instead of the earlier solution used to be either you distribute workloads across different nodes, which individually have GPUs. If you've heard of something called federated learning, which is you can either distribute your model itself across multiple nodes and then do a model parallel training, or if you've heard of something called, um, I think it's data parallel architecture, where you have a big data set, but then you split it up into multiple subsets, and then you train it separately on different nodes, and then you uh, converge all the gradients to make the model learn based on the outputs of all these different sub data sets. This thing doesn't require you to do all that. It handles all of the networking overheads and bandwidth internally. So to a user, it just seems like, okay, let me open a notebook, allocate this entire GPU, and start training my model. And another important aspect to consider is, in software, we deal with the data in data out model quite often, which is how do you bring data closer to the processor right now? Because the way we structure data and how that data flows through data loaders, through different layers of your neural network, you compute a loss function, you get an output. All of that is very data centric. So the pipelines and the kind of software stacks you build around this neural network model completely revolve around data versus how it used to be done before, where you can have data in the cloud and you can somehow bring it through either the internet, or you have your own internal networking infra, bring it to your processors, compute something, and then offload again. In hardware as well, a lot of the networking interconnects have developed around uh, being able to transfer data with minimum bandwidth and with high bandwidth and minimum latency. And if you've heard of the term NVLinks or the Bluefield 3 DPUs, there are entire systems that just do data processing that has been offloaded by the actual GPU. So when we talk about compute today, a very important metric people use is performance per dollar, right? And if you're working with a cloud service provider, the first thing they'll want you to do is provide a good estimate of that indicator. And the only way you can get the most out of your GPU allocation is to not involve any overheads while actually using the GPU or the CPU. And so the infrastructure plays such an important role uh, in dealing with this whole ecosystem. Okay. So this brings us to another interesting point, which is the GPUs and CPUs and all the compute you do while training that's visible to a user is called the compute plane. And there's a lot of stuff happening in the background that the user is just not aware of. For example, what powers on the system, what keeps it alive. And this is called the management plane. There is entire infrastructure that's plumbed in hardware just around the management plane that folks are usually not aware of. But there's a whole emerging uh, research area in how do you implement a management plane such that there is minimum overlap with the compute plane. And in the process, you just have networking protocols and interfacing between the two. So that brings us to management controllers, right? We spoke about the management plane a little bit, but in today's systems, very like systems in data centers of the past, there's a class of dedicated embedded controllers called BMCs, or baseboard management controllers, that have been um, they've been around for a while, but their use case has just got very, very critical, and the sort of workloads they handle have also become very, very critical. These are usually present on the compute nodes that you saw in that video. By the way, if you have any questions, feel free to stop me. I know I'm just rambling on. Um, And yeah, sure.
Question, what is the difference between the general data center and the AI's data center?
It's different in the sense that
Repeat the question.
Oh, yeah. So the question was, what is different between a regular data center and an AI data center? And the main difference is there's a lot of focus given to GPUs in AI data centers, where the main the main outcome expected from AI data centers is to train a model or perform inference. And so your entire data pipelines, hardware, networking interfaces are uh, are constructed to match this GPU-centric way of doing training or inference.
A lot of matrix math. AI has a lot more matrix math.
Thank you.
Sure. Any other questions? Okay. So these are pluggable embedded devices. You'll see them on the compute node of a server. So you saw those gigantic racks with modules that you could just plug out. And within those trays or compute nodes, you can find these guys just hanging in there. It's a spec called DCSCM for anybody who's interested in looking it up. But the main reason it's pluggable is because of how serviceable these need to be. If I construct a data center today, the last thing I want is for my management plane to die, and I have to take down the compute plane for that to fix that. Instead, if I just had something pluggable, just take it off, throw it in the bin, and replace it with a new one. If anyone's been in the server industry, you might have heard of this thing called culling, which is you treat servers like cattle. When something dies, you don't fix, you replace. And that's sort of the strategy here for the management plane, but I think the compute plane is a little too expensive to just throw and replace. So what sort of interfaces do these controllers have? They might be dual or quad core CPUs, not as powerful as the main compute plane, but obviously they need to be able to handle all of the overheads. So they might have GPIO controllers, display controllers, UART. They should be capable of hosting their own servers because it's the main point of contact between a user and the CPUs or GPUs. A lot of people take that for granted. When you have to go work on a CPU's console, when you need to open shell on a GPU or a CPU, this guy's the one that plumbs UART from those main compute systems to the user. And they'll obviously have the usual interfaces like I2C, SPI, USB, probably, and they'll have their own custom Linux kernel running on them. Yeah.
Do they run even the example BMC?
Yeah, a lot of them do. I'll come to that in a bit. But
Repeat the questions.
the question was, do the BMCs run Linux on them? And the answer is most of them do. We'll talk about it a little more in detail because there's a whole open source ecosystem around how you build the software stack for these controllers. Yeah.
Have like CPU and CPUs, or is there any other components that make up the?
There are components that feed data to the CPUs and GPUs as well. Anything that the user interacts with would be the compute plane. Anything that the user can't see would be part of the management plane. So an analogy that I like to think about is it's like the autonomous nervous system, where there's a lot of things like breathing, heart rate, body temperature that's just regulated in the background that we don't really care about. And that's handled by the management plane. So yeah, there are whole hardware parts that are dedicated to this functionality on the baseboard. And these are just listing some of those functions. And an important one is power telemetry. So with data centers coming up in basically literally all parts of the world, we're seeing that companies seem to be holding the currency when it comes to power. And a lot of them are actually overtaking countries. This is from 2023, by the way. So it's going to get augmented by a lot. So a couple of companies have overtaken power consumption just based on their data center consumption. They've overtaken some countries which have a population of more than 10 million people. And I think that's interesting and something we should think about. Okay, so this brings us to the question about, do these management controllers run Linux? So OpenBMC is one such open source framework. It's a Linux Foundation open source project. And it produces an implementation of the baseboard management controller firmware stack. So for those of you who've worked with Yocto, which is a framework to process and customize a Linux distribution for an embedded system, you can think of OpenBMC like a meta distribution. So it gives you the tools to assemble a distro, and you can tailor it to your device architecture based on what you need. Yeah, so it's pretty big now. It's gaining traction. It has 163 repositories within it, with people maintaining it from all the major companies you can think of. It works with upstream Linux. So the kernel is based on what you can just download from upstream. It might use U-boot. It could use lighter bootloaders. It works with Yocto, and it uses something called systemd and dbus, which we'll talk about in a bit. And this is just the software stack that's used. You have a bootloader, which is U-boot. The Linux kernel is most often used. I'm sure there are companies that make their own open source version that's not based on Linux, but the community today seems to be embracing Linux. And in the user space, you have systemd services that run, which do a lot of the scheduling. You might have custom utilities for management. And a lot of these workflows use Boost libraries in C++. So dbus is an important point I wanted to bring up in the Linux kernel. And maybe we'll talk about it a little later.
So on which layer you're putting the security?
So
Repeat the questions.
the question is on which layer we perform security. Are you talking about any specific security measures or just security in general?
Like generally, you want to make sure that your LLM models are not getting corrupted by rogue data or rogue interference. So where are you composing that?
Okay, so the management plane does not directly manage LLMs or deal with data that's going into LLMs. It just orchestrates it. So you can provide instructions to certain components that would act on your behalf, but there's no actual data for training that flows through the management controller. But there's other security in terms of how do you prevent someone from loading their own firmware on the management plane, right? So the security exists in different planes, starting with the bootloader, where you have an image that's attested in a certain way that'll prevent the kernel from coming up if you try to flash a wrong image. Or you can have out-of-band security, which is you have other controllers whose only job is to block other hardware components from doing firmware updates or root of trust kind of stuff. Yeah. So just some very simple rules for how you design software abstraction layers on such controllers. A good model to follow is to define the software as abstracted hardware in your embedded system. So you might have a sensor, and somehow you want to define that sensor in a good enough way in software that it maintains the properties of that sensor, but also adds things like thresholds and alerts and things like that we'll again talk about a little later. But this also helps in visualizing how data flows between components. So you have to talk to like 10 different components on the server, right? You'll have to talk to CPUs, GPUs, FPGAs, CPLDs, whatever is on that board. And by abstracting all of the hardware into software components, you can actually visualize how it flows. By data, I don't mean training data. I'm talking about more like communication type data on the management plane. The second is decision making. So that would be something like, okay, event X has occurred. What do I do? The management controller has to decide whether it wants to alert the user and say, okay, I'm not doing anything. It throws its hands up, or it comes up with the solution on its own, or it finds a path to resolve that issue on the server. And then platform independence. It's very similar to the device tree concept, where you can have specific configurations loaded for different modules. And there's a trade-off between extensibility and platform-specific optimization. Like a good example is Mac OS, right? It's very optimized for the hardware. But because you deal with so many different platforms in AI servers, there's always a trade-off between how extensible it is. Okay, so we looked at dbus a little earlier. And what is it? It's just a low latency IPC mechanism. And it's mostly used for same machine use cases, which means there's a dbus. You can think of it as an application that's running on a system, on a component of the system, which allows all the apps running on that subsystem to communicate. It's not based on message queues or shared cache. It uses Unix sockets under the hood. So it allows you to orchestrate data transfers faster. And it transfers data as discrete messages. So a lot of these IPC mechanisms do byte-based transfers. But in this case, you don't need to worry about buffering or splitting or joining streams of bytes. So it works pretty well for users who care more about message passing instead of passing binary data.
Question.
Sure.
Is that something that competes with like RabbitIQ or other message bus, or is this at a different layer?
This is in the kernel. I'm not very sure with RabbitIQ, but this you can find this as an implementation within the systemd Linux repository. So the question was, does it compute with other IPC mechanisms like RabbitIQ for the folks on Zoom? Okay, so let's assume I open a shell console on my management controller, and there is an app A, which exposes certain properties or wants to communicate with the message bus and in turn communicate with other applications. So there's a utility called bus control that allows you to unwrap the sort of messages that A is trying to pass. And it's stored there for the entire session. So it's not just a message passing mechanism, but it also acts as a cache. And the terms that you would need to know here are the ones in red, which is the bus name. So every application takes ownership of a string that it's identified by on dbus, and a path name, which you can think of like directories, like folders, which encapsulate more data under them. And if I had to go and further unwrap the path name, I would probably see some properties like this. And all you have to know here is there's something called interfaces, which further abstract properties under them. There's something called properties itself, which could be name or any sort of namespace. And then there are signals. So signals are important because they allow one application to get notified if another application has changed something or the state of the bus. So let's take a very simple example. My blue block, the blue block is my management controller, and the yellow block is a CPU or a GPU. And I have a sensor which is connected over I2C to the management controller. I have GPIOs, and I have another interface that we'll talk about in a while. But let's assume that app A and app B both run on the management controller. So you have like a custom Linux distribution that you've built using OpenBMC, and both of these apps belong to that OpenBMC repository, or you can just create your own in C++. This is a very simple example of a template app that you could create on the fly. It makes use of Boost libraries, if you're aware of, and you've coded in C++ before, mainly because they are asynchronous, but also because they maintain context about things like dbus that you can talk to with the IO context object, IO context class. So IO context manages asynchronous IO operations. It stores context for events that need to be processed. And then you can see on line 6, there's something called connection that represents the dbus connection between the app and the message bus. So when you have to pass a message, for example, you would invoke that connection. And then there's something called object server. Object server is the thing that exposes your bus name and paths, and it manages the life cycle of that data existing on dbus. And then you can see some methods like add interface, register property. All of these allow you to populate that big chart that we saw earlier with either property names and values or custom methods that one app can call on another app. And then when you do a request name, it creates that actual dbus connection, which you can later initialize. And then io.run just runs the event loop. Any questions? Yeah. You can just think of it as an executable. That's the simplest. An executable that's managed by a systemd service. Yeah, we'll come to that. There's an example.
Repeat questions.
Okay, the question was, can you explain what an app is in the context of OpenBMC? Any questions about the code? Okay, so if you compile that code, this is what you will get. If I do a bus control on that bus name, it registers a path, which is called /a. Don't worry about the XYZ OpenBMC, that's just convention. All you have to know is it creates a bus called app A bus name with a path that has a /a. So if you can see on line 11, that's what we called it. And on line 8, we have the path and the interface name. And we have two properties, or rather one property, which is value, and one method, which is a random function you can call. Before we go back to the example we were talking about, okay, so I was able to create my own custom implementation of a sensor, for example. I'm considering app A as a sensor. But the only properties I really exposed were values and method, right? But when you operate with real-time systems, you might have to do more things. Like if you have a temperature sensor on board, you have to set thresholds. So if it exceeds, I don't know, 100 degrees Celsius, you need to raise an alarm, or you need to perform a rectification action from the BMC. You might need to set max values. You might need APIs to mark the sensors unavailable if there's an I2C fault. You might need to do hysteresis control, error handling, and those kinds of things. So this is where the OpenBMC libraries or repositories come in handy. They define base classes for most of these extensible objects that are in the management plane. So here I have a repository called dbus sensors that's described in the paths there. which defines a base class called sensor. And if you look at the arguments closely, it's very similar to what our example sensor took, which is just name, threshold, is mutable, which is can you change it, the bus name, and so on. And this provides additional functionality like setting thresholds, max values, and things like that for free. So just by invoking this base class, we now have a fully working sensor. But why do we need to go asynchronous? Because real-time decision making is very important here. We have tens of maybe hundreds in some cases of hardware components that we're trying to manage. So we can't be blocking. We can't be waiting for one hardware component to send us a message before moving on to the next. And this parallel nature mimics hardware organization. So all of your software abstractions keep changing based on how your hardware changes. So from that example, once you inherit the base class, you can see all the properties we need show up, like value, max value, units, things like that. So the max value defines the threshold. And if anything crosses that threshold, we need to decide what to do. Okay, so let's assume, oh, one important point I forgot to cover was that the base class for sensors and the base class for most of these OpenBMC repositories define and instantiate drivers, device drivers. So now I'm talking to the sensor over I2C, right? My base class implementation, my original implementation was just an abstraction. It did nothing. I had to set values manually, but the base class handles doing ioctl calls or opening drivers or opening devices and talking to those devices. So again, I get a fully functional sensor just by using one of those dbus sensors daemons. And it's open source, so you can go read the code, you can go contribute to the code and make this whole subsystem better. Okay, so now let's say we have three paths of communication from the GPUs to the management controller. We already spoke about the sensor, and let's say we have app A that's running that takes care of the sensor. We have app B, which monitors GPIOs. There's another repository called Phosphor GPIO monitor. We won't go into that, but just assume it does the same thing. It monitors GPIOs. If there's an alert, it can signal that something has happened. And a very important concept here is CPERs, which are diagnostic logs that are sent from the compute level to the management level. Let's say there's an event, like a PCIe bus goes down, something breaks in hardware. The hardware generates like a binary dump of things that might have gone wrong. And libcper, which is actually now a Python module, is able to convert that binary dump into a very nice JSON-based format that tells you exactly what's gone wrong, where, and it gives you a detailed analysis of maybe the channels, node number, where it's located, stuff like that. So that's another diagnostic tool you can use to monitor events. And let's say in this example, let's say we've got all three. We've got a sensor reading, we've got GPIOs, and we've got CPERs. And just an overview of the software stack, very generic. You have device drivers in the kernel. You might have a C library on top making system calls. Nothing out of the ordinary, your basic Linux subsystem, and that's what makes it great. I'll quickly go over this. So we spoke about three different kinds of executables or binaries. But there might be cases where we want to duplicate these executables. So you might have a single GPIO monitor daemon just running for a subset of GPIOs. You might have another one running for the next subset of GPIOs, mainly because you want to prevent a single point of failure. If something goes wrong in hardware, it might crash your software implementation of that system. And then you suddenly lose access to all the other GPIOs that were not related to the ones that crashed. And this diagram is basically saying you send all of that data on dbus, and then you have an algorithm that runs to tell you what the next steps to dealing with that issue should be. Right. So in this case, our sensor went bad, or rather, the sensor reports abnormal readings. And the first course of action in such a case would be to determine if the sensor itself is bad, or it's actually reporting valid readings that are beyond the thresholds. And that's the first point can be determined over I2C with our app A or sensor monitor. But then you have different channels of input, right? You have the GPIO, you have CPERs, you have I2C. Now, how do you combine a bunch of these different subsystems to make an umbrella decision on what needs to be done next? This was a simple enough example. You detected an overtemp, so you start a fan. Obviously, there are fans embedded in the compute nodes, and the management controller controls those fans. So typically, how it works today is, and how it's worked in the past as well, is you have different thermal zones defined within a server's compute node. And you have sensors placed within each of those thermal zones. So if you see abnormal sensor readings, you might have like a fan curve that tells you which zone is going bad and how fast you need to run the fans in order to cool it to what degree. So let's say a PCIe lane goes bad somewhere, and that causes the overtemp. You'll probably get a CPER dump of exactly which lanes see an error, and then you might get a GPIO fault reading saying, hey, this lane has gone down, so what do you want to do next? And a lot of that comes under the topic of predictive analysis. How do you predict downtime? How do you prevent downtime? And if there is downtime, how do you report it in the form of errors? And there's a lot of research being done in these areas today. But some very common paradigms that are followed are either you rectify it on system, on the embedded controller itself, but because they are resource constrained, you might want to query like a model running in your infrastructure, but outside the actual controller. So you can have some lightweight models running on the controller itself. So you might have logistic regression, which is the first one for determining if something is good health or bad health. You can use decision trees, very important when you have very heterogeneous inputs. And you can't form like linear decision boundaries. And then you have support vector machines, the third image. This is interesting because you can, let's say you have 100 sensors. You can form an n-dimensional space where each point is talking about how all of those sensors combined react to a specific activity or event that happens. And so you can form a decision boundary based on that n-dimensional space based on the number of hardware components that you have. And that generally gives you an accurate enough estimate of whether there's an anomaly or not. And then you can have external inference. So LLMs are a good way to tell you which components are failing. They can keep track of it based on the data you collect. They can track downtime, and they can also calculate the cost of downtime. Gaussian mixture models, the second image, are good indicators of which part of a cluster or a system, for example, is facing a fault. because essentially you're probabilistically forming a model based on a very large geography of servers distributed over space. So generally, these are used for point detection of which server, which specific compute node in an area might go bad. And LSTMs could be used for time series forecasting. So is my server going to go down 2 hours from now is a good question that LSTMs can answer. And there's a lot of other things that we did not cover today, but these are some of them. Some very important ones are power sloshing. How do you distribute power within a node? How do you care for GPU health? Firmware updates are a big one. How do you transfer? It's not as simple as like an Ubuntu distro where you go and do a software-based update. You log in, you download something and do an apt-get update or whatever. This is more of how do you actually transfer a binary from your management controller to the SPI flash that holds your GPU, vBIOS, SBIOS, and things like that, without which you're completely broke. Yeah, so diagnostics, attestation, performance monitoring are some other things. And there are a lot of technical challenges today. I'm sure you might have thought of a few, but the most important ones are how do you scale this? What we spoke about today is all happening on a single compute node. But in reality, there are probably hundreds of thousands of these nodes coming up all over the world. So if something goes wrong, A, how do you point it to a specific piece of code that somebody wrote? And B, what are the waterfall cascading effects of one small thing going wrong across like an entire data center? And of course, there are resource constraints. People pay you for the GPUs, not for the management infra. So how do you deal with minimum compute on the management side, but still service all of the compute requirements? Long runtime servers don't often reboot. So it's not like your phone where bugs just go away when you reboot it. Every reboot might cost someone like days of running training on some infra. So typically servers stay running for a very long time and you accumulate bugs. And a very big one is petabytes of data. Like there's so much telemetry coming out of these systems that you don't know what to do with them. You can store them, analyze them. How do you model them? These are all new areas, new problems that are developing because we've never collected this much data that's not for the specific purpose of compute. We're just collecting it for smoother runtime of the data centers themselves. So yeah, I think we're a little bit over time, but exactly an hour. So
We're fine on time.
okay,
Question.
this was my last slide. So thank you. I'm available to take questions and we can go into the weeds if you choose to.
What kind of regulatory environment risks that you're thinking that will be kind of coming up because of not simply the trade issues, but more like this massive amount of data, somebody gets their hand on it, they can find out where the vulnerability is.
Okay, so the question is, how do you deal with regulatory issues based on privacy for data?
Privacy for data, but the backend, the telemetry data that is being created. I mean, somebody could tell us, oh, you do this thing and it spikes the compute node, right? You do that thing, it messes up the server, right?
Exactly, yeah.
But that data is very highly regulated. Like you said, it's massive amount of data.
Yeah.
Problem is, nobody has space to keep that much data.
Yeah.
And right now, probably there are no regulations that says you have to keep it for 1 year, 6 months, 7 years. You have to do it within that country, within the continent, whatever it is, right?
That's a really good question. And most countries have their own data laws that prevent all of this data from even going outside the data center. So they have their own infrastructure that supports storing this data, and they have their own timeline. So they can wipe it every year, every 2 years. A lot of them wipe it every month because you instantly catch issues. So yeah, storage is a big one, but more importantly, how do you analyze so much data?
Does your BMC software measure the latency of your network or your VM link, or something like that?
It can measure latency on the management plane. It doesn't measure latency on the compute plane, which is how fast you can transfer training data. But yes, like how fast can your network link up on the compute node is something the BMC would manage. Or even just setting up the Ethernet connection to the compute node for people to log in through shell is something the BMC would manage.
So, and you usually, where is the CPU and the GPU? GPU is acceleration, right?
Yeah, it's on the same baseboard. All of these components are on the same board. Yeah.
Can we put the GPU on the NIC, different interface card?
That's a good question. So today, the way GPUs are constructed is they're all distributed in the sense that you can have multiple such baseboards. There's no reason to have it on a separate NIC, but you do have a NIC that will abstract all these GPUs as a single GPU. So they all talk to each other.
Can you draw?
I might have an image. Let me see. Okay, so here. So a lot of these slots contain compute nodes, right? So I don't have a cursor, but these things. And all of those house the GPUs. So sorry, I can just show you here.
All of those blades are server blades.
Yes.
So you have GPU and CPU.
Some of them have. Some of them are just switches.
Just switch. Or there's a top of rack switch and the server which has GPU and CPU.
There's multiple switches in the rack.
Exactly. But if I use a NIC, if I use the acceleration in a NIC,
Mm-hmm.
where it will be here?
So the NIC, there's a spinal cord at the back that connects all of these racks.
So you can have a card that's the back which has the NIC.
Yeah, like there's a whole different infrastructure that does this, but yeah, it is connected to your
Does
point.
NVIDIA use this infrastructure which uses NIC?
Yeah, it's their own NIC, but yes,
But they have to use it.
yes,
They have their own NIC.
yes.
But does it sell well?
That I can't answer, but
Because when I look at the different marketing reports, they have different feelings. Some are saying they don't sell well in enterprise, or they sell well in telco. Some are saying, no, I'm confused.
Okay.
Maybe you can shed light on it.
Yeah, I don't know about it, but if I did, I'd be
You're not
hoping
involved in sales, so you're not able to speak to sales.
exactly, yeah.
They are actually called post-bus adapters. They call DPUs. They're quite extensively used in this.
Yeah, the Bluefield trees.
Many of that.
So what do you work on? Oh, I see. So you work on Bluefield?
Yeah.
Okay, nice.
The internal communications, are they all encrypted, or do they have chips that are kind of doing it, or it's open communication once you go past a certain layer?
Okay, so the question is the communication, I can speak for the management plane, is it encrypted? And the answer is yes, because we have our own protocols that do it. So unless you have a decoder on the other end, a lot of it cannot be intercepted.
Question. So there had been in the past map reduce where there was a lot of redundant computation, assuming that things are noisy or messy.
Mhm.
And then you kind of reconcile based on agreement. But here is it assuming that everything is highly reliable, so they don't need redundancy in computation.
Where would you use something like this? Would it be on the
Well, I mean, for managing computing. So
Okay.
in the past, like 2004, MapReduce was coming out for cloud computing.
Right.
So for cheap cloud nodes that weren't necessarily highly reliable, you could farm out the same computation 3 times. And see if they agree 2 out of 3 times that you use that. But there was some extra redundancy for high performance computing. Just because things were messy when you get to thousands or hundreds of thousands of nodes being fault tolerant. So for fault tolerance for these large scale NVIDIA systems, do they just expect high reliability and there's no redundancy for fault tolerance?
I actually have no idea, but that's a good point. So
Okay.
I want to learn about it
If you
too.
have like hundreds of thousands of GPUs, then and some computation goes wrong,
Okay.
then I guess that's a situation I was asking about.
I think he wants to say.
It's a very expensive thing to have a redundancy in this, so the map reduce kind of a thing, we are a long way away from
Right.
needing, I mean, using it very expensively.
Okay. So the expectation is just having everything be highly reliable.
Yes, these are actually highly managed environments. It's not actually like an arbitrary workload, that kind of a thing, right? So people know the job they're going to run and things are set up accordingly.
Okay.
Can't like other GPUs in the cluster like pick up data and just wondering whether maybe like extra capacity or like probably GPUs itself can pick up data.
I mean, that would be a design in your software. If you design redundancy, you can build some redundancy in there as a software developer, I guess.
Okay, any other questions?
So like architecture wise, when you're looking at it, like now are they separating out like AI data centers specifically, or is it like they're really extending the normal data center and just adding a wing or a branch or whatever it is to make it a AI data center?
There's a lot of commonalities. For example, BMCs and the entire management plane have been around for ages. So that has been extended into these AI servers, but a lot of the focus on GPU-centric infrastructure is new. Like the DPUs, for example, are new. NVLinks switches that are primarily used to move data around very quickly is a new concept. And of course, there's a whole security infrastructure that backs it. Yeah.
One question about these BMCs. So how different are the BMCs that are used for the AI service from the general purpose service? Like are they different? Because I think the way I see there's much more functionality, I guess, the AI server than BMCs.
Yeah, in terms of hardware, they might be similar.
Please repeat the question.
Okay, so the question is, are BMCs different in AI servers versus conventional servers of the past? And the answer is there's a lot of similarities, especially in hardware, because we use the same interfaces, a lot of the same standard networking buses, protocols, but we manage a lot more things now. And there are specific applications, especially those for GPUs, which have only come up after AI servers. And so a lot of those services we write internally and they're proprietary, and those go on to the BMC. So the software stack is different, but we also are realizing that we need more compute on the management side. So you do see more powerful cores being used for manageability in general.
Because you were talking about few machine learning based algorithms to do some kind of
Yeah.
predictive analysis and all. So that would obviously mean that it would require more computation power itself on the
Right, exactly.
right?
Yeah.
So you're trying to say that you're going in the direction where you want to see how you can improve that as well.
Right. So there's a trade-off between actually making expensive chips, which are baseboard managers, versus just running those models off-prem. Yeah.
Do you know like if CISA or any other federal organizations are issuing any security? Because I don't work in this side, I work on more on the compliance side.
Okay.
So from the compliance side, right, whenever there is a big issue, we do get like direct emails from CISA and whatnot through federal government, right? But is there anything going on in this space where if they find out there is a vulnerability or something, then they, of course, at the company level, CISO level, they are connecting. But to the end user, to the person who owns the data center, the company that owns the data, they actually communicate with this thing.
Okay, so the question is, are there any federal regulations that govern the security posture?
Like CISA is a federal organization, right? That sends on all this communication whenever there is a vulnerability found.
Okay.
And they want to immediately fix this, whether it's
Oh, sure.
0 day or a
Right,
critical
yeah.
or a high or whatnot, right?
Yeah.
But is there something that's coming on these chips? Because these chips are literally like selling at the price of gold, right?
On the management side, yeah, there are. I didn't relate to the name, but there are security threat models that have been published online in the past, but they've all been rectified so far. And there are security teams that work on monitoring these and plugging the holes.
And this controller is a piece of software running on the CPU, right?
No, it's separate. It's a separate embedded controller.
Or hardware.
Yes.
Controller developed by NVIDIA. Intel.
This is open. The firmware stack is open source, so anybody can make their own embedded controller. It just depends on the use case.
It's a hardware component.
Yes.
Who developed?
Manufacturers. You can have your own. You can make your own.
NVIDIA does its own.
Maybe they outsource a little bit of it, but
I work at a company that makes them. I work at a company that makes them.
it depends on the use case. We have so many platforms that we might manufacture some for specific platforms.
Communication between the management and controller, is it like through conventional system bus, or do you have like a specific bus, or do you use like NVIDIA?
It could be conventional protocols, so I2C, USB, I3C, SPI, all of those. The question was, what sort of interfaces exist between the management plane and the compute plane? Okay, great. If there are no further questions, thank you so much for sitting through this. I'll hang around, so if you have any questions, we can still talk and network. Thank you.
Thank you very much.